So we left off yesterday talking about transformations. That's moving your graphs up, down, left, and right. It's also squishing them or making them wider, changing their shape. That's the theme of, or that's what I mean when I say transformations. So in this practice problem, we have a graph. Here we have your original graph, the equation of a line. We'll sketch it roughly. Let's say this is 6. Here is a slope of 1/2. Oops. Okay, so it looks something like this, right? Oh, why does that keep happening? So then, if we were to transform it in part A over here, we add 2 to this, we see that that moves everything upwards. It goes up to 8. It'll look something like this. Notice the slope is, wow, why does that keep happening? The slope remains Okay, slope remains unchanged. Okay, no idea why that keeps popping up. Wow. Okay, what is wrong? I think I'm writing too high, that's why. Then the second part, over here, let's draw our original line again. There's your 6, here's your slope, positive 1/2. And now we're multiplying everything by 2. I'm like wondering if people joined. Give me a second. So I have to use this waiting room and admit them in. Okay, seems like everything's good. Alright, so you have that same line and everything's being multiplied by 2. Algebraically, that looks like 2 times that 1/2 x plus 6. So that gives you 1x plus 12. That's our new equation, y prime, or here's our original y, okay? So things, 12. So things look like this now. Things have moved up. Let's call this one 12, and now it became steeper. And we can repeat that for these other ones down here, these transformations where our change is now next to the x, it's inside, all our inputs are being changed, versus these, it's modifying all the outputs of our functions. So when you sketch those, we'll see that, okay, let's just do maybe this one. This one moves our original graph where we have 6, and you have your slope of 1/2. This one moves it left 2. 1, 2, like so. And it doesn't change the slope. Okay, that's what we talked about yesterday. And then here, the next couple of slides are reviewing some of these properties. If you went through the classwork on like slide 18 or something like that, you graphed them out in Desmos, you followed along and tried some things on your own. If you were with me yesterday, you would have seen these properties appear. So let's say for adding k, we had a parabola, something like this, right? Y equals x squared. And if you added k to whatever this equation is, like plus 1, then that graph would look like, okay, it moves up or down. In this case, it moves up. There's your new vertex. And then it opens in the same width, like that. Maybe I'll use that in a different color. There's your plus 1. It shifted upwards of 1, and it goes like this. This behavior was the same for lines, it was the same for quadratics, and then exponentials also work this way. You can have a quick sketch, something like this, right? An exponential curve, wherever your y-intercept is, your new graph, when added 1, shifts it up, still has that same curvature. I did a better job drawing it this time. That's your transformation, right? This is the one that moves it up and down. Things make sense. This one, it gets a little weird. As we see from yesterday, we knew it moved left and right. And if you investigated it further with a couple more graphs of the linear form, quadratic form, or the exponential form, you should see that, oh, it's actually the x-intercepts that move left and right. The growth stays the same, and the initial value changes. Let me see if I can demonstrate that with a parabola. Going again to blue. Say we had this one, like so. Let's call this y equals x squared plus 1. And then in red, let's investigate maybe this one, plus 1 squared, like that. Hope it reminds you a little bit of vertex form. You'll see that it moves over. So now it goes like here, and it opens up like this. Wait, wrong way, my bad. So this is the mistake that is very common. Change my pen to being red. This one actually moves it to the left a little bit. So for sure you see that change in the initial value, its y-intercept. And if I were sketching it more correctly, you would see that left and right change. For exponentials, it's a little different. The initial value stays the same. The growth is the one that changes. We can give a short example of that. Y equals 2 times 3 to the x. If you were imagining, okay, now it looks like y equals 2 times 3 to x plus 1. Your growth rate now has like an extra 3 in there. 3x, and then if you were to break it up in terms of exponents, there's an extra 3. Okay. A couple more participants. Okay, so algebraically it looks like that, and then you can sketch out the curve in Desmos or by hand yourself. It's 2 out of 4 transformations. This is adding k next to the x, modifying your inputs by a factor of k. Here, like a quick example, because I see that a lot of you weren't here yesterday. I'll go into a bit more detail on these transformations. When you're multiplying by k, for the lines example, right, like that, it's your original line. If you were to multiply things by k, the growth and your y-intercept change. So let's say this was the equation y equals 2x, and then, no, let's do like plus 1 or something, right? And then you had your new graph. After the transformation, you multiplied everything by 2, it becomes 4x plus 2. So your y-intercept moved up here, your slope got even steeper. It's like that first example I talked about. My graph is not fully correct. Shoot, like that. That's a little better. X-intercept stays the same. You still got the same zeros. You still have the same roots. And again, the quadratic is very similar. Exponential, it does something funky, as growth here stays the same. When you're multiplying it by this constant, it only changes the y-intercept. And if you observe that from the y equals like 2 times 3 to the x, if I multiplied all that by, let's say, 4, you can see that only the initial value is affected because all of this is repeated multiplication, right? See the 8. The growth rate still remains 3. Then over here, the weird one where you multiply your input by a factor of k, I think this is the harder one for me to demonstrate. We'll go through the exponential. Actually, did we do this one already? Did I write this one twice? No. No, okay. Well, we'll demonstrate this one with the exponential. So there's your exponential graph, y equals, let's say, 2 times 3 to the x. And now we go to this new one. Now it's times 2. So then your equation looks a little funky. 2 times 3 to the x times 3 squared. We get y 9, 18, 3 to the x. So then it moves like up here, and it gets even steeper by a certain value of an exponential. My hand's cramping from holding the stylus. So you could study these, like more specifically, what I hope you take away from this is that, okay, I can understand new functions, these complicated changes bit by bit, by adding, multiplying, and looking at the inputs and outputs. When we go back to chapter 8, when we study vertex form, it's nothing but this transformation idea. Shifted left, shifted right. Do I make it wide or do I make it more narrow? Okay. So the second part of our lesson after the review is working on the inverse of a function. Okay, we have these original functions. Here we have f, here we have g. How do we change them, flip them upside down? How do we undo them? How do we recycle them so that the inputs and outputs are swapped? So we go back to something familiar. On this slide, it's all the stuff. If you want to follow along and write, you can. The next slides, I'll write down my answers and post this on the slides. But the main idea here is that we have a function machine, right? Part A is what we're familiar with. Then parts B, C, and D walk us through this new idea of an inverse of a function. What is the inverse given some kind of relationship? So for part A, we have this function machine. What's this part A? Darn it. Okay, I've left myself little room to write, so I guess I have to do it really small. Okay. So over here, there's our original function machine. We put in a 3, the function machine does something, and then it spits out a 13. When you put in a 4, the function machine performs those same steps, and it spits out 16. It gives us a third point. When we put in a -3, it spits out a -5. So in words and with an algebraic equation, we want to figure out what this is. It is in fact linear, so it is an equation of a line. So I'll just write it down. The equation looks like 3x, and then you got to figure out its starting value, which I think is, let's see, 7. No, it's 4. Okay, so how did I work through these two steps? I made an assumption that it was linear based on these 2 points. I notice it's a +3 pattern to go from 13 up to 16 with a change of 1 to get from 3 to 4. And then I saw that, okay, if I go backwards by an additional 6, it maintains that same 3 pattern. So that's our rule. And specifically for this rule, the English steps are to first multiply by 3, then add 4. So that's how I would say this equation in words, and you'll see why this matters when we try to find its inverse. So then here, the new stuff, right? This guy, Ambrose, really wants to work for this company that produces functions. There's an opening in the recycling department for which he would like to apply for. Here's the new math idea. In this department, outputs are put into inverse function machines. The inverse function, written f with a little -1 exponent of x, undoes an output to recreate its original input. So this is the new stuff. Okay, whatever is inputted this way and originally was outputted, think about this as going in reverse, right? This arrow now goes the other way. So if you put in 13 into the inverse function machine on the right, what number should come out? What would happen if you put, to have come out 16? And then what happens if you put into this reverse function machine, this inverse function machine, -5? Okay, so over here in this picture, it kind of answers the first part for us. When we input a 13, it spits out a 3. Okay, it's like drawing little arrows going this way now for this function machine. So that means if I input a, where is it, 16, a 4 should have popped out. So for this one, oops, 13 gives 3, 16 gives 4, and -5 gives -3. So far, so good? Okay. So we'll get lots of practice with this, right? For now, in the function machine example, imagine if this is my original, okay, then the inverse now changes this arrow to go like this, and then it spits out, right, input of 13, outputs 3. Input over here with the picture, input of 16, and then it goes through this machine, and then it outputs 4. Over here, input of -5, outputs -3. You see that undoing that opposite relationship here? Kind of? Yes, no? Okay, maybe. So we'll do that once more. If we were to write out the steps explain in Word what steps the inverse function machine are to undo the original. Well then, for this one, it goes because we added, we're going to subtract 4, then divide by 3. Okay, notice that's here, going the opposite direction, and also undoing these operations, right? Where we will lastly, we added 4, so we're going to start by subtracting, undoing that, and then we divide by 3, because the next step here was multiplying by 3. And we can say that in symbols, f inverse of x. First, we subtract 4 from our input, then we divide by 3. So up here is our original function. Here's our inverse function. Okay? Now we have this one. It gets a little bit more complicated. We're still going off that function machine idea. So here's a new function machine, and it tells us in words what the steps are. So our input here is 3, and we're going to figure out what this function machine outputs. So input of 3, start with 3. First step, 3 times 5 gives us 15. The function machine does some more. The next step after that is subtract 8, which gives us, well, let me indent it over a little bit. 15 subtract 8 gives us 7. And then the third step, 7 divided by 2 gives us 3.5. So in this first part, what equation would she write? For g of x, we can summarize these 3 steps using symbols. G of x equals, first multiply by 5 to our input of x, subtract 8, and then divide this all by 2. That's our equation. These are the steps for each of those equations. And if the output of what is the output if 3 was put in? So then for this question, g of 3 we'll see is the same as 5 times 3 minus 8 all divided by 2. You'll see that that is 3.5. So that's reviewing some function notation. It reviews these 3 steps, translating English into words. Here's the new stuff. Kimberly was asked for the steps of the inverse machine named G inverse of x and its equation. What did she write? So for this part, we got to do the opposite. Do the opposite and reverse the order. So think about these 3 as steps over here. Originally, we were going down. This was number 1, 2, and 3 for the steps. And now we're going to change those to being 1, 2, and 3, and then reverse the operations. So where we once first started by dividing by 2, our first step to get g inverse of x is to multiply by 2. Okay. We then add 8 to undo the subtraction by 8. And then we divide this all by 5 to undo this multiplication by 5. So then this part is what she wrote down. So I'll write that out in words for the steps, right? First, multiply by 2. Second, add 8. Third, divide by 5. Are we kind of getting the hang on things? The hang of things? Can I get some nonverbal feedback? Okay, cool. So now we'll get a bunch of practice, and maybe conceptually you're still a little shaky. With some symbols, with some more practice, maybe you'll see the idea. Oops, I did it again. Okay, let me move this, all this stuff down over here, because I meant for this part to be the answer slide. Okay. So now here's more practice. There's 4 problems here, and you can work through each of these on your own. If you're watching this later, then you would pause the video, work through these. I'm going to solve these 4 problems down here. Okay, so for part A, we'll write through the steps, right? So we can pay attention to order of operations. Here, our step was first multiply by 4, then subtract 12. Our inverse has to do the opposite. We have to go the other way, and also we have to undo the operations. So notice the symbol here with the little negative 1 exponent, that's the inverse of n, of x equals, well, if we started here by subtracting 12, we have to add 12 and then divide by 4. Okay. For this one, in part B, j of x, right, and the order goes subtract 7, then divide by 10. So in symbols, that looks like finding the inverse, we do the opposite. X times 10 plus 7. Down here, notice there's more and more steps. It helps to write it out because we want to follow through with order of operations even when finding the inverse. So for this one, p of x, what do we do first? Do we multiply by 4, do we cube it, or do we add 6? Right, that order really matters here. Order of operations says to follow the parentheses first. So our first step is add 6. Do we cube or then do we multiply? Order operation says then cube it. That's raising it to the third power. Multiplying it by itself 3 times. And then our last step, right, write it out, 2, 3, is multiply by 4. Okay, that's when it could have got you if you didn't follow through order of operations, and you would have gotten a different, you would have solved for the inverse of a different function. So to find the inverse, we'll start here and work our way up. So we undo a multiplication by 4. We have to divide by 4. Okay, so we undid the last step that was from our original. To undo cubing, or raising to the third power, we can take the cube root, like this. And then to undo an adding of 6, we subtract 6. Okay. It also looks like x divided by 4. Remembering our fractional exponent is the same as the cube root, like that, minus 6. And for part D, you can work through this on your own. I'll just write up the answer for good reference. Oops, I messed up my first step. Okay. So for these 6 problems, let me show you a different way to solve for the inverse. So the steps are to find the inverse. Start with the equation using x and y. Okay, step 1. So for this one, we're going to ignore this function notation. We're going to pretend like f of x is y. One symbol is going to be a lot easier to manipulate. Then 2, you're going to switch x and y. So this problem now becomes x equals 2y plus 3. And then step 3, solve for y to get your inverse. So then the steps look like, okay, x and y are now swapped. I have to get y by itself. We got to practice our solving skills. So we got to take away 3 from both sides, and then we divide both sides by 2. So ta-da, here's another way for us to find our inverse. There's part A. This is how I learned it in algebra originally. This is how we find the inverse using just symbols, with no need to write the words. Let's do this one, so I can leave some extra practice for you. And if you look back at the slides, I think I posted the answers from the previous section. Once I split it up amongst 2 sessions, you'll have all the answers, I hope. Okay, so let's practice these steps for this one. Y equals 1/2 x plus 5. Switch x and y. Okay, then we solve for y. So first we subtract 5 from both sides. And to get y by itself, to undo the multiplication by 1/2, we multiply both sides by 2. And thus we found our inverse. For part D, I'll rewrite it because I couldn't find the square root symbol in Google Slides. So this looks like the negative square root of 3 minus x. Okay, and for these kind of problems, this method's a little more helpful. What would happen in a test if you only put the answer? Oh, that's fine, because right now they're not that complicated. If it says find the inverse and you can do it all in your head, by all means, just write down the inverse. For these more complicated ones down here, it's going to be helpful to show your work like I am doing here, because sometimes that order of operation with all this opposite idea may get you. Okay, so then where am I? Switching x and y, negative square root, like that. First multiply by negative 1 on both sides, so now we have negative x equals the square root of 3 minus y. Square both sides, negative x squared equals 3 minus y. Subtract 3, oh gosh. Okay, I need more space. Okay, and then we're going to subtract 3 from both sides. Now we have negative x squared minus 3 equals negative y. And then we multiply both sides by negative 1, so we have negative x squared plus 3 equals y. So then for part D, our answer looks like negative x squared plus 3. Oops. That one's a little tricky, part F. That's our inverse for D. Half points. If that wasn't answered, I wouldn't pay any attention. Okay. I did it once more. I need to move this down. Okay, well, that's the practice for today. A shorter idea of inverses. Okay, you can do the problems I didn't do as more practice. Inverses, you'll see it later in Algebra 2. Definitely in pre-calculus and calculus if you decide to take those classes. And it's a neat idea. Okay. These will be uploaded along with this video. See you again tomorrow. We'll do some statistics, practice that. Okay. All right. Take care. I'll give you some more practice. The COVID review has been released. Please try to do it on quizzes if you can. I don't think you can skip around.